Hello everyone and welcome back to PC Retro Programmer. It's been a while since there's been any new video content on the channel, and I recently decided to get back to the three main programming series that I started here. So this video is part of the CGA Graphics programming series for the CGA Graphics card that was used with the original IBM PC. It had a 4-color graphics mode with a resolution of 320 by 200, and we previously saw how to draw pixels, lines and circles. And when we came to circles, we noticed that they looked a little bit squashed. And this is because pixels are not actually square on CGA, but a little higher than they are wide in the ratio of 6:5. So if you want to draw something that looks circular on the screen, you actually need to draw an ellipse that's squashed in the other direction to compensate. And so that's what we're going to work on in the next few videos on the channel. Now, we're not going to restrict ourselves to a ratio of 6:5. We're going to allow a much more general semi-major radius of R pixels and semi-minor radius of S pixels. And this will allow us to draw ellipses with any ratio we want. So it'll be much more general than what we need for drawing circles. We'll just pick a ratio of 6:5 when we want to draw a circle. Now, we are going to restrict ourselves to ellipses with axes that are vertical and horizontal, so-called standard ellipses. But of course this is enough for drawing circles for sure. Now, the algorithm that I'm going to use is one that I've developed based on the midpoint circle algorithm. It's really hard to find a version of this for ellipses online, and so I just did it myself. Now, I did do a video on the channel about the mathematics of the midpoint circle algorithm, and I did it in enough generality there that you can see how to do it for ellipses as well. Now, I won't go through that derivation, but when you go through that process, this is what you end up with. Now, this is a pretty straightforward algorithm. You can see there's some variables and constants that are set in the beginning here. There's a loop here, this while loop, and another one at the bottom, and there's a little correction that occurs in the middle here. So this loop here draws all the pixels from the rightmost point of the ellipse down to when it starts moving diagonally. There's a little correction for the diagonal. Sometimes you need an additional pixel in the diagonal direction, and this just makes sure that happens. And then finally you have the loop that takes the ellipse from the diagonal round to the bottom of the ellipse. And so really this just draws a single quarter of an ellipse, or a quadrant of the ellipse. And this is exactly what we did with circles, and then we reflected that quadrant about the axes to get the other 3 quadrants. So that's exactly what we're going to do here. Now, there are a couple of problems that we're going to have to deal with in this algorithm, and that has to do with the size of the values that we're using. R and S are the semi-major and semi-minor axes in pixels, and if we're drawing the largest possible ellipse on the screen, these could be half the width of the screen and half the height of the screen. So R could be anywhere up to 160 and S could be up to 100. Now, those will fit in 8 bits just fine, with a little bit of space left over. But down here we square those values, and so we'll actually need 16-bit registers to hold the squares. But down here it gets even worse. We take one of those squares and we multiply it by R again, and then by 2. And it turns out that this value, in the worst case, only just fits into 24 bits. So how to handle 24 bits on a 16-bit CPU? Now, obviously we're going to need 1.5 registers for this, and it's actually worse than that because these variables d and y delta also change throughout the algorithm, and those also can go up to almost 24 bits. So we're going to need a total of 4.5 registers just for these 3 variables here. And we still need an accumulator for doing some arithmetic. We need the pixel color, and we need the offset that we're up to on the screen, and some other information as well for pixel drawing. So it seems that we're going to run out of registers. We're not going to be able to hold these values C and A, which are 16-bit values, or the X and Y coordinates directly in registers. So to work around this, we use a technique called self-modifying code, we'll pre-compute these constants C and A at this point here, and we'll actually write those values directly into the assembly code at the points where they're used. And then they'll be available when they're needed without having to be stored in registers. And you can do this with anything that's a constant. We won't be able to do that with the variables, of course, because they change throughout the algorithm, so they will have to be in registers. And we're not going to store the x and y coordinates explicitly anywhere. We'll just keep that information implicitly in the offset information and the other information that we store for pixel drawing. So it turns out that everything will fit, and in this video I'm going to show how to do this first loop here in assembly language. So this will allow us to draw roughly 1/8 of our ellipse on the screen. So let's take a look at the code for this episode. This can be found in my GitHub repository as a link in the description, and this is ellipse1.asm. And the first thing that we're going to need to do is to allocate our registers. Now, obviously we're not going to have enough space to store absolutely everything in registers, so some things have to be constants, and they'll be written directly into the code as I explained. So that includes the values C and A here, but there's another thing here which is actually a constant, and that's the color of the ellipse. That doesn't change throughout the algorithm. So we're actually going to write that into the code as well. But you might remember that when you draw pixels in CGA, each pixel is just 2 bits in a byte in video RAM. And so we need to do some bit twiddling to get the color into the right position within the byte before writing the byte. And this is quite tricky to do if we store all the information that we need for that. So we actually use a trick to reduce that information down to just a single byte of information, which we'll use as a mask. So basically the trick is to repeat the color information, which is just 2 bits, 4 times in a byte. So we'll have the same color for all the pixels in the byte, and then we'll use a mask to mask out the individual pixel that we're actually interested in writing. And so the only thing that we'll actually need to store, which is going to be changing as we're moving pixels across the screen, is the mask. So that enables us to save 1 byte, and that turns out to be exactly enough. As I mentioned, we have 3 variables, d, dx and dy, and each of these requires 1.5 registers. And I just set it up so that the high byte is in an 8-bit register and the low byte is in a 16-bit register in each case. Now notice that I used the BP register here. Now normally that's required for accessing the arguments to the function when you call it, but once we've finished with these arguments and everything has been pre-computed, we don't need to use BP anymore, so we can actually use it as a general purpose register, and so it will actually double up its function. It will be used for 16 bits of the dy value as well. We use AX as our accumulator as usual. That's a very standard choice, and DI for our offset, another pretty standard choice. And the only register really left over after I made these choices here is CH, and that's the one that we're going to use for our mask. Let's start with our setup code, and the first thing that I do is put the CGA segment address in the ES segment register. And then the very next thing is to compute this color information byte that I was talking about, that has the color repeated 4 times across the byte. Remember, each color is specified by 2 bits, and so you can fit 4 pixels in a single byte. And remember that we'll have a mask byte, which will mask off one of those pixels as needed. So to compute this color information byte, I put the color in the AL register, so the color will now be in the bottom 2 bits. And to duplicate that, I shift the value left by 2 bits and add it. And I just do this again and again, and that gives me 4 copies of the same color information across AL. Now this color information byte is needed by the code below, and I don't want to take up a register to store it in the meantime. So I'm actually going to write this constant directly into the code at the point that it's needed. So this is called self-modifying code. So the constant is in AL, and I write it directly into the machine code, at a location that I've labeled below called ellipse color 1. So I just labeled an instruction below, and I figured out from the machine code that the actual constant occurs 1 byte after the start of this instruction. So that's the byte that I need to modify. So let's go down and have a look at what this looks like. So ellipse color 1, here's the label here. It's labeling this instruction, and this is the 8-bit value that I'm loading into AH. And so I just overwrite this constant value here, which occurs 1 byte after the start of this instruction. And then instead of using this random value 012 that I put in to keep the assembler happy, it'll use the value that I overrode it with every time this code is run. So that's the self-modifying code trick, and you can use it anywhere on the 8088 and 8086, but you have to keep one thing in mind, and that's the prefetch queue. On the 8088, it has a 4-byte prefetch queue, and so you might be modifying code that's already been loaded into the prefetch queue by the CPU, and so modifying the code in memory is not going to make any difference. So you really need to modify code that hasn't already been loaded by the CPU into its prefetch queue. So for the 8088, it's a 4-byte prefetch queue, so you need to modify code at least 4 bytes in advance of your current position. And on the 8086, it's a 6-byte prefetch queue, so you need to go 6 bytes in advance of your current position. Now, the next thing that I need to do is to set the offset value for the first pixel that I'm going to draw in my ellipse. And this is exactly what we did in the case of the circle, so the code is the same. I won't go through it in detail. The ellipse is centered at x0, y0, and the first pixel is the rightmost pixel, which is r pixels to the right. And this is exactly what we did for the circle. The other thing I need to compute along the way is the mask byte for that first pixel. So the mask will be 2 bits set to 1 to select that pixel, and I have to shift it into position with this code here. And again, that's exactly what we did for the circle, so I won't go through all the details here. But now that's all set up, and the offset computation finishes here. And the next thing that I do is to compute 2 constants that are needed in the code below. These are our constants C and A. C is just S squared, and so I put S in the AX register and multiply it by itself. And now I use the self-modifying code trick to put this constant in the 2 places in the code where I actually need it. Now I looked at those, and in both cases the constant occurs 2 bytes after the start of the instruction, and the same thing happens for when I need the A constant below. So let's just take a look at that. Here's where A is used, and you can see that it's just an instruction that loads that constant into the BP register. This is a 16-bit value, so I just put a random 16-bit value here to keep the assembler happy, but this will be overwritten by the self-modifying code above that I just showed you. So that deals with our constants, and the next thing is to set up our variables. And I've been a little bit tricky here. One of the variables I actually already computed since it starts off at one of the constants that we already computed, and I already put it in the right register, so no need to move that. The only other one that I need to actually compute explicitly is the dx value, which starts off as 2 times c times r. Now c was already computed and I put it into the BP register for safekeeping. I don't need to access any of the arguments to the function after this point, so it's safe to use BP for this. And so that's the value c, and I multiply it by r, which happens to be in the bx register, and that gives me c times r. Now dx needs to be set to twice this value, but remember that this is a 24-bit value, so I need to do a 24-bit shift left by 1 bit. And that's what these 2 instructions do. Actually, this is a 32-bit shift, but it doesn't make any difference because the top 8 bits are irrelevant at this point. The way this works is to shift the low 16 bits left by 1 bit, and there's 1 bit that's shifted out the top of AX, and it actually ends up in the carry flag. That's what this shift left instruction does. And I need that bit to be shifted into the bottom bit of the DX register. And that's what the RCL, the rotate through carry left instruction, does. It'll take the carry flag, shift that in as a bit at the bottom of the DX register here, and it'll continue shifting all the other bits of the DX register left by 1 bit. So that does our multiplication by 2, and so now our DX value is set up, and the only other thing that I need to do is set some bytes to 0, and now all my constants are set to the correct value and I'm ready to go. And I'll start off with the first of the loops in our ellipse code. Now the first thing this loop calls for is to draw a pixel on the screen, and remember that we're maintaining a color information byte and a mask precisely for this purpose. So we just AND these together, and that selects the 2 bits for the color information that we need in the appropriate position in the byte. Now we need to write this into video RAM. The first thing we have to do is to read the byte from video RAM and zero out the 2 bits that we're going to modify. So this is a very standard way of doing this. We just negate our mask and then AND it with the byte from video RAM. And now we're able to write our 2 bits of color information in using an OR instruction and write the whole byte back into video RAM now that it's been appropriately modified. The next thing that we need to do is to update some values. So we have to add dy to the d variable, and this is a 24-bit addition. So this can be done with a 16-bit addition for the low 16 bits and an 8-bit add with carry for the high 8 bits. Then we need to add the constant 2a to the dy variable. So 2a is actually a 16-bit value, and remember we wrote it into here with self-modifying code. I didn't point it out above, but we did actually compute 2a. There was an additional shift left of our a value above before we wrote it into this constant here with self-modifying code. So we add that 16-bit value to the low 16 bits of dy. We've got nothing to add to the high 8 bits, but we still need to do an add with carry with 0 in case there was a carry out of this addition. And then finally we need to move down the screen by 1 pixel by updating our offset. And this is exactly the same code that we used for the circle to do this. So now we come to this if statement in our algorithm, and the first thing we have to do here is to compare d with dx divided by 2. So we have to compute dx divided by 2, and this of course is a 24-bit shift right by 1 bit. And the way this works is we have to do the high 8 bits first, and this will shift 1 bit out of the bottom of DL into the carry flag, and we use this rotate through carry right instruction to shift that bit into the high bit of BX and then continue the shift. Now you might wonder what happens to the BX value. The bottom bit is just going to get shifted out, so is that going to get lost? And it turns out that it isn't, because the dx value is always even in this algorithm. It starts out as an even value, and we're always subtracting 2c from it during the algorithm, so it's always even at this point. So nothing's lost when we shift out that low bit. Now, the first thing we have to do is to compare our d variable with this dx divided by 2 that we just computed, and this is a 24-bit comparison. And the way that you do this is first look at the top 8 bits of each of the values, and this might already tell you if one of the values is going to be bigger or not. And if it is, you can just jump off immediately to wherever you need to go. But if they end up being equal, then you need to look at the low 16 bits of the values and do a further comparison to see which value is actually really larger. And so this is how you do a 24-bit comparison. Now there are two cases. There's the case where we execute the body of the if statement, and there's the case where we don't. I'll deal with the case where we execute the body of the if statement first. The first thing we have to do in the body is to undo the change that we made to dx. Remember, we shifted it right by 1 bit up here, and we need to put it back to its original value. So this is a shift left by 1 bit. It's a 24-bit shift, and I've already been through how those work. Then we need to update some values. We subtract the constant c from dx, and this is very similar to adding a 16-bit constant, so I won't go through the details here. It's the same thing. And similarly, subtracting dx from d is just a 24-bit subtraction. That's done with a 16-bit subtraction and an 8-bit subtract with borrow. And again, we subtract c from dx once more. And finally, we need to move left by 1 pixel. Now, this is the code that we used in the circle routine for this. We may need to update our offset, and we certainly need to update our mask as we move 1 pixel to the left. So that's how we accomplish that. And to finish off our loop here, we need to do a 24-bit comparison of dx and dy. And if dx is greater than or equal to dy, then we jump back to the beginning of the loop. So this is again a 24-bit comparison, and I've already been through how that works, so I won't go through it again. So now we get the other case. This is where we don't execute the body of the if statement. And again, first of all, we need to undo that shift of dx that we did, and then we're able to finish off our loop using this 24-bit comparison, which I just showed you. So that's actually it for this algorithm for the first loop, and that's all I'm going to show in this video. We're actually done now, and we can run this code and see what happens. So I'll just remind you that to assemble and link this code, we use tasm to assemble it, and we use t-link to link it to make an executable, and then we can actually run this and see what it looks like. And you can see some pixels appearing there, and this is approximately 1/8 of our ellipse, although as I said, because it's a squashed shape, this is not really 45 degrees in an ellipse. It's much less actually. The next quarter of the ellipse will be much longer. It will come right around here, and that's what we'll work on in the next video.